All right, hello everyone, and welcome to the final part of V versus T graphs. If you remember in the last session, we kind of went ahead and we used our V versus T graph to just find the displacement equation. We also found another few equations along the way. I thought it would be cool if we can go ahead and use a few of them in word problems and actually try to figure out how we can go ahead and create, basically values and actually pertinently find these values in a realistic situation. Let's go ahead and actually do this one. I thought it would be interesting. John is in his car, okay, and he starts out from out of a green light from rest. Okay, now I can already see a few highlighted words, but let's just read this through. He then proceeds to accelerate at a rate of 2 meters per second. If he travels for 4 seconds, what is his displacement? Now, notice, since this is asking for displacement, I have an acceleration, and I also have like a term like from rest. That does tell me a few things, okay? Number one, I'm going to have all three of these values. I also have a time here, seconds. So let's go ahead. What's the equation I can use? Well, let's go ahead. If I know, and if I remember from last time, that's going to be my displacement equation. In other words, x, or my total displacement, is dependent on my x naught, plus my initial velocity, or my v naught, times t, plus 1/2 a/t squared. Now that I have this, I can go ahead and figure out a few values. Now, number one, I know that I'm starting from rest. In other words, my v naught is 0, right? Because I start from rest, I'm not moving. So my v naught, 0 meters per second. Okay, I want to find my displacement. And for all intents and purposes, we can say that this is delta x or things, but I want to find my total displacement. I'm going to make the assumption that my x naught is 0. Okay, because I do want to find my total displacement, because I just want to see how far I've moved. So I'm going to say my initial velocity. I'm going to just set my starting point from that green right. I'm going to say my x initial was 0. So I got two terms that are 0. And in fact, if you look at the equation, I can just cross these two out. I do have an a, though. I have an acceleration, and that is 2 meters per second squared. So 2 meters per second squared. Okay, so notice I set my 0 point, and I have this. So I'm going to go ahead and create my equation that my displacement, okay, is 1/2 or of my acceleration, which is 2 t squared, or just say it's 1t squared. Okay, let's go ahead and plug in some values. And notice I've used this equation. I just plug in 4 seconds, which is my time, right? That was my final value, right? I have a time of 4 seconds. And basically, I'm using my displacement equation, and I'm just kind of plugging in t's, okay? In this case, I didn't have a velocity or an initial point, or I chose to make my initial point 0, just setting out my number line. And when I did this, I went ahead and I got this. And then after, let's go ahead and plug in 4 seconds. So x equals to 1 times 4 squared, which equals to 16 times 1, obviously, though, is 1. So that makes 16. Okay, which means I have moved 16 meters. Okay, in other words, John has moved 16 meters. And notice that is the use of that displacement equation, which I think could work. All right, and you see that actually works out pretty well. And because it's a polynomial, that squared here is kind of the thing that actually makes it accelerate real fast. And it allows you to see the effects of acceleration within a movement such as this one. You notice he starts from 0, but he gets to 16 meters, which is pretty impressive in the span of 4 seconds. All right. we have this one. I'm going to go ahead and erase this, but go ahead, take a screenshot if you want to. Although this is YouTube, so you can always pause. And let's go ahead and try this again, but let's try it to solve some problem that's a little more difficult and actually will take a little more time. Okay, let's go ahead and I'm just going to go ahead and be sure everything's erased. And I'm going to just go ahead and move down a few slides. Okay. Let's assume that we have Jane now. All right, and here's another problem. You have Jane. She's running a 100-meter race. And if she can accelerate at a rate of 0.2 meters per second from rest, her initial velocity is 2 meters a second. When will she finish? Notice I have a when will she finish, okay? So that's kind of the question here. We have our, x equals to v naught t plus 1/2 at squared, or if we expand it out, it's x final equals to our initial point, or initial placement, or x naught, plus v naught t, right? Plus 1/2 at squared. Okay, now in this case, we're looking at her acceleration as she runs this race, and we're giving several values. So this is our equation. Let's go ahead and take a look at our values. We know that, number one, the total distance she has to run is 100 meters, okay? So maybe I didn't need to expand it out that much, but I know my delta x is going to be 100 meters. Okay, so I'm going to be using this version of the equation just to make things simple. Okay, I know that my acceleration, if I look at it, so this is my displacement, here's my acceleration. So I know that her initial velocity is, so I know her acceleration is this, is 0.2 meters per second squared. And I notice that this woman has a velocity, an initial velocity of 2 meters per second. Okay, that's okay. Now I can go ahead and I can do this, right? If I go ahead and fill in this, right, I notice I get something. I end up in an interesting place, right? I go ahead and I get 100. And I want to solve for time, right? But you notice what's going to happen here is I get 2t, right? Plus 1/2 at squared, or actually this is actually 0.02. I'm sorry, I need to erase that. I was just kind of moving through. So 1/2 0.2 t squared. Now you notice now we have t here, right, and t here. That's going to cause a problem for us. So notice in the end we're going to end up something like this, right? We're going to end up with we're going to end up with 2t plus 0.1 t squared. Okay, notice we can't really get around this. We got a t squared, and then after we got 100. And you see, now we're in trouble because, I mean, either way you slice this, you're always going to end up with a t. This is a polynomial, which means I technically have two answers out there in the universe, which means I'm going to have to actually figure out what exactly is going on. So first of all, let me go ahead and put it in polynomial form. We have, and if you remember what polynomial form is, it's like a t squared plus b t, or b, whatever variable you have, plus c equals to 0. Now I'm going to go ahead and put it in that form just to go ahead and make those terms simpler to me. So I got 0.1 t squared plus, and this is my b term, right, 2t minus 100 because I need to move 100 to the other side, so that way I can get 0. Now you see here, I'm going to get answers here, but, it's going to be very different. So I can obviously go through polynomial theorem. I'm going to go ahead and actually cheat a little bit in this example, and I'm going to go on and move on to my best friend Wolfram alpha. I'm going to take this into consideration. Okay. So we're going to go ahead and go on to Wolfram alpha, and Wolfram alpha is going to spit out 2 answers to me using polynomial theorem. Okay, so I'm just basically going to plug this into Wolfram alpha just as is. And actually, I'm just going to go ahead and do this, and then I'll come back to this slide. So we got 0.1 t squared plus 2t minus 100 equals to 0. And that's the polynomial form. Then we're just going to say Wolfram alpha. And Wolfram alpha is going to just do it for me. Okay, I was hoping that would do it. One. Okay, I can see I have the tab here, so let's go ahead and just take a look at the tab. And when I go ahead and do this, I have this here, right? And you can see the polynomial curve here. This is the form that we put in. And notice when it actually does it, it spits out this, right? Yeah, and you can see here, we unlock 2 solutions. One of them is a negative. Now, because it's a negative, this saying this happens negative 43 seconds in the past. Obviously, Jane hasn't won this race in the past. She's winning this in the future. So we need to look for a positive future time. And that'll be this one. So at 23 seconds, or 23.2 seconds into this race, she's actually going to win this race. So she'll create that displacement. She'll win, get that time. So our answer is right here, 23.2. So you just have to plug in to Wolfram alpha all those terms, just like so. Your A, B, and C terms, and you'll go ahead and naturally get your answer. All right, and that concludes my series on acceleration. Go ahead and good luck. I will go ahead and see you guys next time.